Hello, I'm Yehan Liu, and welcome to my lab2 report, which is about motion of a falling object. The purpose of the lab is to observe and analyze the motion of a falling object, comparing real-world data with two computational models, one that includes only the effect of gravity and another that incorporates both gravity and drag force. By comparing these models, the lab aims to explore concepts such as terminal velocity and the effects of drag on the object's motion. And the fundamental physical principles involved in this lab are Newton's second law of motion and the concept of drag force. The lab demonstrates how gravity alone affects an object's motion when falling, and how the inclusion of a drag force, which opposes motion and is proportional to the square of the object's speed, influences the object's velocity and potential terminal velocity during free fall. Mathematically, it can be expressed as this also. And here are some equations involved in the lab. In addition to the first three formulas which we used in lab 1, this lab also involves formulas for calculating the gravitational force and drag force. Then let's introduce the two models involved in the lab. The first one is the experimental model, which is based on real-world observation. The motion of an object was captured and analyzed using tracker software, extracting its position and velocity over time. And here is my video. Then the next one is computational model. It's that a computer simulation was created using the initial condition of the object from experimental model. Here is a preview of the result. We can see that the three lines stay almost coincident at first, but gradually grow differently. We're going to analyze that later. Then let's see the experimental setup. So the system is a paper ball I dropped, and the surroundings are air resistance and gravity. The air resistance is also the drag force in this lab. Then about the initial conditions, the system mass, I just set it to be 1 kilograms because it does not affect the result. And about the system position, at first, the tracker shows it's 0.1050, and the system velocity at first is 0. The starting time is 1.9 seconds, and the delta time is 0.033 seconds. This picture shows how I use tracker software to get data from the video. The first case in computational model is that we only evolve gravity. So the assumption we made here is that air resistance or drag force was assumed to be negligible. And you can see I applied the initial condition to the closed strip code. Then in the case when drag force is evolved, we just set B equals to 1, which is the proportionality constant for drag force, which in case 1 is 0. Next, let's take a look at the results of the lab. I made a line graph corresponding to the three sets of data obtained from the different models. As you can see from the graph, the three almost overlap at the beginning, but as time changes, the gap between the data set that only consider gravity and the data set that consider both gravity and drag force becomes larger. This is because the drag force counteracts some of the gravity force, and thus the falling speed is relatively slower. To my surprise, the data of the experimental group almost overlapped with the data group that only considered gravity, which should be caused by the fact that the paper ball I used was compressed very tightly and was less affected by air resistance, drag force. If I had used an object with a larger contact area with the air, the data would have been relatively closer to the data set that considered the drag force also. There are two possible errors. The first one is the surroundings error. Is that when recording the video of the object falling straight down, there might be some airflow from the surroundings, like from the air conditioner, that would affect the motion of the object. And the second one is the accuracy error, is that there could be some inaccuracies when tracking the objects using the tracker. Then here are my answers to the follow-up questions. For the first question, the terminal velocity occurs when the drag force pointing upward is perfectly balanced by the gravity force pointing downward. This means that F net is 0 and the object is in uniform motion. Therefore, the velocity versus time model with resistance will predict the terminal velocity. It can be observed from the velocity versus time graph that the velocity slowly becomes constant at the end of the graph. And for the second question, I think the end velocity of an object initially thrown downward is the same as the end velocity of an object initially dropped from rest. The only difference is that the end velocity of the object initially thrown downward is faster than that of the object initially dropped from rest. Thanks for watching.